Our objective, obviously, we're trying to, at this point, just decompose fractions. I mean, the objective you see up there for 7-4 is huge, but all of it has to do with, can we decompose a fraction? So like we talked about yesterday, the only time it's not going to be just one constant for a numerator on any of these fractions is when we have an irreducible quadratic. This is reducible. It is already reduced. Notice how there's no squared inside the parentheses. It's an x to the first. So now it's a linear factor. So what we would do now is think, again, you're always connecting, especially with algebra and anything in that, connect it to what you know from the past. And what we know from the past is if we're going to put these together, we would need to get a common denominator for all of these. So this one has an x, but it's going to need 2 of those x minus 2's. So it would be a times x minus 2 squared. And I don't need to bother with the denominator because what I'm doing right now is I'm making a common denominator and thinking through that process. Then I go over to b and I realize, well, this has 1 of the x minus 2's, but it's going to need an x and 1 more x minus 2 to make this work. And then our little c over here, it already has 2 x minus 2's. It just needs an x. And now what we want to do is simplify this so that we can see where are my x squared terms, where are my x terms, where are my constants, and how's that going to work. And remember, we cannot distribute this power of 2 because there's subtraction taking place here. You can only distribute a power when there's pure multiplication or division. So we actually FOIL that out and get x squared minus 4x plus 4. X minus 2 times x minus 2. Or you memorize the formula for squaring a binomial. And here, well, 2 ways you can do it. You could distribute the x and then distribute the b, or you could distribute the bx at the same time. So that will be plus bx squared minus 2xb plus cx. Now I still have to go back and distribute the a, and normally we do multiplying and dividing from left to right, but it doesn't really matter in this case. Too many people on phones today. Get them turned off. Pay attention. Because now here's what I'm looking for.
Why didn't you just put in the a first time with the x? Like you did with b.
Oh, it doesn't work that way. Order of operations. You have to do powers before you do multiplication. So, and most people aren't going to be able to do this in their noggin, so I didn't want to skip a step and go right in there. Okay? Cassie? We need 2 of them. Remember, we're going to build them up. All right, so now here's what we want to do. We need to see what all the squareds are. So let's go through. We've got a squared term here and a squared term here. So that tells us that ax squared plus bx squared has to equal. Well, let's go up and find out what the squared thing was. There it is. It has to come out to a -1 x squared. Then we go back and we just find the stuff with x's. So that is -4ax plus, minus 2bx, 2xb, 2bx, it doesn't matter, plus cx equals. And then we go up to the top of the fraction. See, that had to come out to a 2x. Those are all the x terms that have to add to that 2x. And then last but not least, we have our little constants. Well, that's it. It's our only constant. That's good news. 4a has to equal 4. So here's what we do. And I'm going to go through the motions, even though this one's a little bit easier than what we need. We take out the x's, or sorry, in this case, the x squareds and the x's and all that good stuff. And any of the variables, we don't need those for matrices. So if we're going to set this up as a matrix, we just need the coefficients for a, b, and c. So it would be 1, 1, 0 has to give us -1. -4, -2, 1 has to give us 2. And then 4, 0, 0 has to give us 4. But this one's actually really quick to do algebraically. So you could do the matrix, do RREF. You could use inverse matrices. You could use this for your first matrix, take the inverse and take it times that matrix. But if we just do this, drop the variables, just keep the A's and B's. That last one very quickly tells us that A is going to be 1. A has to be 1. And then we kind of do our back substitution. We realize we can't go to the green one yet. The green one has too many variables. But boy, if I go back up to the top one in the blue, subtract 1 from both sides, B is -2. And now that I know A and B, now I can go back to my green equation, my second equation. Do a little simplifying. -4 plus 4 is 0, so C equals 2. So now that I've found A, B, and C, if we're doing partial fraction decomposition, we're supposed to go back and say, okay, here's what the fraction with A on top would look like. So go back up here. And I said x under the first one, x minus 2 under the second one, and x minus 2 squared under the third one. So A over x plus B over x minus 2 plus 2 over x minus 2 squared. Here's what drives me bonkers about these, and it's because of what you do in calculus. We leave this plus a negative. I can't stand that. It's one of those things with simplifying that drives me nuts. But we leave it, and it's because of what you need to do with it in calculus that we do not change that plus negative to subtraction. So that's the partial decomposition part.
What do you do with it?
You just leave it right there. Oh, in calculus, this is the Ruth doesn't like it. Even when last year, she asked the students when they came in whether or not they'd ever heard of limits, and she started in as though they'd never heard of limits before. And then some of the kids said, "So you don't talk about limits last year?" And she was got to save all the good stuff. Yeah. All right, so that's partial fraction decomposition. That's what we have to do. Break it up. Now, remember, they said yesterday, if you want to check this, easiest thing to do, go all the way back up to the top, graph this bugger, go all the way down to your answer, be very careful with all your parentheses, but graph that, and it should go right over the top of the first graph. I mean, that's the way we know they are equivalent. They're exactly the same. They'll graph the same. So let's see what else they want us to do. Alternative method. We're not doing alternative method.
Did you need to make a matrix for that?
You can.
Okay.
Like I said, that one was just so easy algebraically. I don't know why you'd. I mean, maybe it's just me because it takes me so long to punch things in the calculator, and I often punch them wrong. You know, it just seems silly to do it with this one. But for tougher ones, oh yeah.
Okay.
Yeah, make a matrix, hand it over to the calculator. Like I said, either RREF or inverse matrices. Get your answers right away. Because these are involved enough without trying to do everything by hand. And as I mentioned, we're not going after alternative method. This is good enough. If we get good at this, we're solid. Alrighty. Whew! Look at that one. Ooh, it's a monster. Alright. So I look at my denominator and I realize it could be something over an x plus 2. Well, that's a linear factor. So that's just A. Could be that there's just an x minus 3 on one of them. That's also. 1B1 that actually had the x minus 3 squared on it. But again, that is a reducible quadratic, so that gets a linear factor.
We aren't learning that alternative.
Oh, so that was still in your packet?
Yeah.
Oh, Mrs. Peterson talked about taking that out. She just left that in there. Yeah, we're not going to do the alternative. This is the best one. Yeah, this is, if you can get this down solid, you're good. Now you'll have everything that you need. It's one of those things where originally there are 3 ways to teach this, and we just went to Mrs. LaRue and said, do they need all 3 of these methods? And she said, nope, do this one. So this is the one we're doing. Now, we need to build these up. Notice the denominator was already factored. Every once in a while, we're going to see a couple of them today. And if we do have an irreducible quadratic up here, then we have to put a linear function up front, up on the top. So we do cx plus d. But it's done exactly the same. Exactly the same. So our little a out in front will need what? An x minus 3 squared. Our b would need what? Yeah, both of them. X plus 2 and x minus 3. What's our c going to be? Oh yeah, that's good news. Just c x plus 2. So we have our LCD when we look up here. It's all broken up and factored. So now, order of operations, we've got to take care of the powers first. We can go ahead and do the multiplication of FOIL in the middle. That's not going to bother anything. Again, multiply and divide left to right, but it's not going to be. So then you distribute your A and your B because we're trying to see which ones will give us our x squared, which will give us our x, etc. Drop a little half step that I did in the last problem. So I'm going back to check for the x squares. But I'm not going to write down ax squared. I'm just going to write a. And now I'd have to scroll up. You take a look at that fraction. X squareds have to add up to what? Got to be a 5. Let's go find all of our x's. Again, you don't need the x's. What do we want our x term to come out to be? 21.
Isn't b supposed to be negative?
Oh, thank you. Negative 6a minus bx. Yep, I was looking at the wrong one there. Plus cx. And finally, our little constants, which is what's left up here. All the little constants have to come out to 13. See how this one's a little tougher. And we didn't end up with A equals B equals. So this one, we probably want a matrix and let the calculator take care of it for us. So, 2 ways to do them. Let's do this one first with our REF, reduced row echelon form. And if we do another one, then we'll do that with our inverse matrices. So 1A, 1B, no C's, and a 5. Negative 6, negative 1, 1. And negative 21. 9, negative 6, negative 2. Nope, positive 2. 9, negative 6, positive 2, and 13. And we're going to RRF that. I'm not going to bother bringing up the calculator on the smart board because we have already done this with that calculator. If somebody's been gone, we can reference that. So second matrices, I'm going to edit this one in there. It's a 3 by 4. And go ahead and punch the numbers in. Back to the main screen. Matrix math. RREF. And then pick the name of the matrix, whatever it was you put it in for. And there we are. There is our result. Now I want you to tell me what that means.
A equals 3.
Right.
B equals 2. C equals 1.
There we go. So we've got 1A equals 3, 1B equals 2, and 1C equals negative 1. What do we do with that? Backtrack and put it where we said it was supposed to go. Now again, that's going to take me too long to scroll. So what do we have A over the top of? Just x2 plus 2. And then it was the x minus 3. So some of them more involved than others. But in the end, if we put it into a matrix, no matter how involved it is, we can figure out what the A's, B's, and C's are. Now, somebody had asked, and yeah, we better start seeing maybe a couple that don't necessarily have just that constant up there, and that's what's going to happen in example 4. Example 4 shows how to find the partial fraction decomposition for a rational function whose denominator, in fact, does have an irreducible quadratic factor. But this one is start to finish. They didn't even do anything in the denominator for us there. So it says, find the partial fraction decomposition of that little monster right there. So, do we have a GCF that we could pull out of all 4 of those terms on the bottom? Right? It has 4 terms. How do we generally try to factor stuff with 4 terms? Grouping. So we could take x squared out, and that would make it x minus 1. But what do you pull out of x minus 1 if you can't pull anything out? 1, because this is division. Now remember, that x minus 1 showing up twice doesn't mean that it's a factor twice. It means we just tricked our brain into seeing that it was a factor. So x minus 1 is definitely one of our factors, and the other factor is the other 2 leftovers. Because what we just did was divide them out, and we want to know what they would be if we multiply them back together. Numerator, we don't do a doggone thing, and that's because the power in this one of the denominator is greater than the power of the numerator, so we're not going to try and divide or anything like that. All right, so here we are, x squared plus 4x plus 1 over x minus 1 times x squared plus 1. There's our irreducible quadratic. X squared plus 1, you can't factor that any further. So what we're going to have to happen with this one is something over x minus 1 plus something over that x squared plus 1. Well, with linear factors, it's just a constant. It's A. But irreducible quadratics, that's where we have to give it a linear. Whoops, no, I shouldn't use A again, for goodness sake, I'll be like the book. Bx plus c. So linear means we're using that x to the first in there. All right, well, let's get after it, huh? There's our a. What's it gonna need? X squared plus 1. We've got our now bx plus c. What's that gonna mean? An x minus 1. So see how it turns into FOIL in the past. Once we had everything written out, it was mostly just distributing. But this one is going to be a little FOIL. So ax squared plus a, distributing our first one there, plus, now we do our FOIL, bx squared minus bx plus cx minus c. That almost looks like a parenthesis. So let's group our squares together. Group our x's together. And group the constants. Yeah, I can see you're already doing it. Go back and say, okay, what did we have here? What was our square root? Well, we had 1 x squared. And 4 for the x. And 1 for the constant. So this one, there's so many ways to do this one algebraically too. Does everybody see it? You know, you could just use those two together. You could use substitution. There's all kinds of things. But like I said, I want to do at least one inverse matrix thing with you again today. So what we do with the inverse matrices is we say ax equals b, then a inverse times b will give us our answer. So we're going to use a coefficient matrix, which means just the a's, b's, and c's. So we'll have 1, 1, 0, 0, negative 1, 1, 1, 0, negative 1, times our a, b, and c, s equal 1, 4, 1. And what we'll do is we'll get those two matrices in there, bless you, and then we'll use that inverse button and multiply it times the matrix 1, 4, 1. Yeah, Art.
Is there any difference between reduced echelon form and doing the coefficient?
You'll get the exact same answers in the end if you do RREF versus the inverse. It's just a matter of do we have a problem on the test that says use the inverse matrices to blah blah blah, and another one that says use RREF. You just need to know the difference and how to use them as two separate matrices for inverses.
So if it doesn't say one is it like one different than the other? Or does it
I
say
always
that?
use RREF because it's faster. You know, using one matrix is always faster than using two. Oops. And these are answers just pop up because we had a 3 by 3 and a 3 by 1. Our result vector is a 3 by 1. I'm running out of room. And you do the same thing we did before. You'd say, well, where does my A, B, and C go? Well, my A was supposed to go over x minus 1. can see where they should go in this linear expression up here. So negative 2x plus 2. Same thing for checking. You know, like it says, checking your algebraic solutions, you could check them with matrices. You could also check it by graphing. You know, there's all kinds of different ways to do it. And like this says here, they recommend, if you don't get told, using RREF, reduced row echelon form, because it's just faster. You know, one matrix, one RREF, to check those. We have another one, decomposing a fraction with a repeated irreducible quadratic factor. Well, that's different. At least they factored it for us. That was nice of them. So let's see. So one of them is going to have to be x squared plus 1. And the other one will have to be x squared plus 1 squared. Well, what's the part we have to be careful of? It's irreducible. So what's going up here? Ax plus b, exactly. Both of them have to have the linear factors. So I'm just going to do ax plus b and cx plus b. Well, then we just do what we know, which is if we really were going to do this math, we would get the common denominators going here. So ax plus b, that linear factor, is going to need another x squared plus 1 if we were going to build these fractions up. Oh, because if you are building up these fractions, it's possible that one of them just had an x squared plus 1. Because if we multiply by x squared plus 1 on the top and the bottom, we have this common denominator. It is also possible, though, that one of them already had this as a denominator. So we have to take every single power that we see as a just in case to build these up. For instance, if we had an x cubed, we're going to have to put something over x squared, and something over x cubed, because all of those could have been the denominators when you started. So we do the same thing with this, even though it's a little more involved. Oh, the numerator part? They always give us that. Yeah, that we're going to be given. We're not going to do anything with that unless this power is bigger than this power. The degree of this polynomial is bigger than we need to divide. But that'll be for something different that we're going to do. Alrighty, you're probably well on your way here, right? Because we don't need to multiply the cx plus by anything. So, little FOIL. Looks like so. Oh, a cube. Well, did we have a cube? We have a cube. Well, that's kind of good then. If it's the only one, that has to be that one, doesn't it? So, A equals, what was our cube coefficient? 2. Squareds, even better. Only one of them. And that was a -1. And we have A plus C. And our x terms came out to 5. And constants. B and D. What was our constant? Yeah, 0, it's not there. I wouldn't do a matrix with this one. Does everybody see it? Yeah, this is going to go super fast algebraically because we already have that A is 2. B is a -1. And B plus D equals 0. Put the B in here. Go back after the A plus C, 2 plus 3. Give me that. Good morning, Mrs. Cedarholm. Hi. He is not here. What was it? It's a field trip or something today. Okay.
I'll go in this place.
Okay, you got it all written already? All right. Yeah, I know you don't need that thing. So, we got 2x minus 1 over x squared plus 1. Done, right? See how they're all kind of the same. I mean, you just have that irreducible quadratic that you have to think your way through. Oh, we're fine. Excellent. We'll almost catch up today. Here's what I want to do. I want to skip the next page and go to the last one so that I'm sure we're all done with the partial fraction stuff. Okay? Write the form of the partial fraction decomposition without solving for the constants. Woohoo! That means all we have to do is make sure we've got the A's and the B's and the C's all set up, and we don't have to actually do it. But is it factored as much as it can be? Questionable. Two numbers that multiply to 5 and add to 2. Rats. Irreducible quadratic. These are factored. All right, so first denominator would be our x squared plus 2x plus 5. What would that mean on the top of it? X plus b. Next denominator would be what? Just 1x minus 4. Yeah, this is the part that stinks. So let's see, we got A and B. There's C. D. E. F. Whew. One more to go. So what are we going to do with the top of x plus 3? Just a g? Don't need gx plus something? Nope. Linear factor. Well, that would be an interesting problem to do, wouldn't it? Yeah. We're not doing that one. We just want to be able to do the setup here and say, okay, we know what we would do. I'm not looking forward to x minus 4 times x minus 4 times x minus 4 times x minus 4. You know, that brings back Pascal's triangle and expanding binomials and all of that into this mess. But we would be capable of doing that. Let's talk about what we need, which is another part of our objective, and that is, does this help you when you're graphing? It does. Each part of the partial fraction decomposition of a rational function does play a central role in the analysis of its graph. We can use it to describe the end behavior of a graph at its asymptotes. But we better see this first so that we're sure that's something we can do. All right, so it says investigating the graph of a rational function. Compare the graph of f of x equals 2x squared plus x minus 14. Those with your heads down, don't start breaking this one apart. This one's not done that way. Over x squared minus 4. Here's the reason why. We're going to use that, but it's secondary. The first thing we need to notice is these powers are the same. And when we graph, remember that we can find the behavior of the graph as it approaches 0 if we actually do the division. So this is division. So that we can see how is this graph going to behave as x approaches 0. So we look at it and we say, self, how do I get x squared to be 2x squared? Multiply by 2. Now the 2 are matched up with the other 2, so I'm going to put my little 2 right up there. And then I'm going to change the signs and add 0, x, minus 6. So it'll be 2 plus, because we can't keep going, we can't multiply x squared by something and get x, plus a remainder of x minus 6 over x squared minus 4. So here's what that's telling me. It's telling me that as I get closer to 0 with this graph, it's going to behave more and more like y equals 2. So it should kind of flatten out or something by 2, which kind of tells me that's probably an asymptote for that portion of the practice. It's not going to happen. And then, once we have this, the next part they want us to investigate is, okay, what happens if you do the partial fraction decomposition for that remainder? What do you see when you do that? So if we go after this, what happens? And there's some really cool stuff that happens graphically when you do that.
How do you know it's not a whole? Because if you put the 2 in on the bottom, it becomes 0. You divide by 0, or
Right?
you just
Probably going to be a vertical asymptote, which we'll see in the very next step right here. Because we're going to try and factor that denominator. What's it factor into? It's the difference of 2 squares. So those 2's are actually vertical asymptotes. X equals -2 and x equals 2. This is kind of putting everything we already knew about graphing and a little bit more. So, partial fraction decomposition of that little bugger. Well, x plus 2, x minus 2. Do we need x's for any of our numerators? No, that's lovely. So A times x minus 2, because that's what we would need to build that up, plus B times x plus 2. And we'll find our decomposition now. Ax minus 2a plus bx plus 2b. And that means a plus b is going to equal 1, because it was 1x minus 6. And our constants, negative 2a plus 2b, will equal negative 6. Anybody else notice that everything in that bottom equation is divisible by 2? I might make this go a little bit faster. I'll leave the top equation alone. Divide by 2. I'm not doing the matrix. Add those 2 together. You get B right away. And then you think, well, A plus negative 1 equals 1. That'd have to be a 2. So, we had that 2 hanging out in the front because we already divided and got the 2. But now we also have a 2 over x plus 2 and a negative 1 over x minus 2. And like I said, there's a lot that we could review on these problems from things that we already know how to do. But what they want us to see is, how is this 2 over x minus 2 related to the final graph? And how is this negative 1 over x minus 2 related to that final graph? So what we're going to do is we're going to put each one of those partial fraction pieces on a graph and then graph the whole thing and see, does that help? Having that information, does it give us something? So 2 over x plus 2 that and say that's going to have a vertical asymptote at negative 2. So I could just pick some numbers to the right and left of that and see what I get. So if I put negative 1 in here, yeah. Remember, that was from our division right at the beginning. When we divided, we got that 2. That's going to tell me how the graph, the entire thing, approaches 2 as it gets closer to 0. All right, so putting a negative 1 in here, negative 1 plus 2 is 1. We're going to get 2. So negative 1, 2, that's tiny. There. Put a 0 in, 2 over 2 is 1. And we know these are hyperbolic because we have the division, so that one's going to go down. Plop a negative 3 in. Negative 3 plus 2 is negative 1. 2 divided by negative 1 is negative 2. So 3, negative 2. 4 in. Negative 4. Negative 4 plus 2 is negative 2. 2 divided by negative 2 is negative 1. And again, because we know the behavior of these hyperbolic graphs, that graph's done. Now we want to graph negative 1 over x minus 2. Where's the vertical asymptote? 2. So what number should we track? Stare at it and hope it goes away. That thing is not moving. 0 and 1 would be good. Yeah, they're right next to that. So we plop a 0 in here and we get a positive 1/2. Plop a 1 in, 1 minus 2, negative 1, negative 1. And we can see it is going up. There's our hyperbolic branch right there. Plop a 3 in on the other side. 3 minus 2 is 1, so at 3, negative 1 divided by 1 is negative 1. 4 in. 4 minus 2 is 2, so we'll get negative 1/2. Yeah, there's our hyperbolic branches. Now what we want to do is see how does that compare with the overall graph of the whole thing. So we went back, way back to the beginning. And we would say, to see those vertical asymptotes for this, we would want to factor this in x plus 2 and x minus 2. If we want to try to see where the x-intercepts are, we might try to factor the numerator. And just to save time, you guys know how to factor. Let me peek and see if that was factorable. It wasn't factorable. It's an ASCII. And you could always do b squared minus 4ac, and if it doesn't come out to be a perfect square, then you know it's not factorable. So this does have asymptotes, vertical asymptotes at 2 and negative 2. And remember when we did that division and we got it 2? That tells me that between here and here, my graph is going to approach negative 2. So it's either above it or below it. It's approaching it. That's what that tells me. I need to see what the rest of this graph is going to do. Now, normally we take the time to make tables and all of that, but let's just grab the graphing calculator so that we can get this in and see what she looks like. Don't forget to use parentheses for the numerator and then parentheses for the denominator. So, like I said, just to get us where we need to go, I'm not even going to bother grabbing the table. What we're supposed to see is this. Look at these graphs. See how this behavior is the same as this behavior. This behavior is the same as this behavior. And this was approaching 2. It's definitely not getting all the way down there, but it gave us something to focus on. So this is additional, besides all the stuff we already knew about graphing, which is huge, which shows us that this does give you an idea of the end behavior. And obviously I'm running out of time to write down that end behavior, so we'll start there tomorrow. But that gets us pretty doggone close to caught up. But obviously, just to be fair, I'm going to give you a couple of days. Let me scoot this one up. because we fell behind. Give you an extra day or two here. For those two. It is amazing how much we can find out about graphs from just digging really deep algebraically. All the things that we could possibly do algebraically to the graph that give us pieces of information.
Emo Thursday, all right.
It's like that long. Flannel Friday. I haven't worked with boy.
Yeah, possibly yellow soda.
Yellow's all around. Oh.
And again,
I was blown away. I was
the best.
Of course I did. Got you. What is a vampire favorite? Oh, you said that it's
Dude, don't still all the red ones. No, you're done.
That's what the Dutch is.
Because I get shaky. No.
Let's start with
Maybe I'll bring
Fuller
it
T
back.
and then T.
Yellows are.
I want that.
That's true though.
That was a good one.
How do you get an alien baby to sleep?
I want to.
You rock
I
it.
had to split with somebody, but it was still like crazy amount.
What is a buccaneer? Expensive corn.
have a great day and thanks for hanging in there. That was a long section.
I don't get it.
It's,